So let's continue here into these print results. So now we're interested in looking at the class. So we just did these four, but now we want to look at this one, this index 5. So let me run this and it'll be very clear. So how many unique labels do we have? And this is what the unique function is doing, which returns the unique elements of the input tensor. So we only have one of class 2, but if we had more, we will also only get one for 2. But if we have other classes, then of course we'll get those classes as well. This is a different way of saying how many classes have I detected? And then here you're summing the classes that you have. So in this case, the class is 2, and we only have one detection for that class. And we can do the same here. You can see that n, well, n is 1, and of course c is tensor of value 2. Now here we're going to add to our existing string, we're going to add more to it. And in particular, we're going to add the name. So let's do it here first. Let me run this. And of course, I didn't save all of them. Names, we have 80 classes. I only went all the way to 9. But basically, what this is doing is looking at the names dictionary, and for C, which in our case is 2, 0, 1, 2, basically give me that string. So if we run this, now we've added one car at the end. Okay, now we're going to start writing some of the results. We can print this again, nothing new here. So we're going to look at all our detections in reverse order. In that case, we only have one, but we're going to get our xy, our confidence, and then our class. And then of course, our class is 2. Our label, as we did earlier as well, is the car. The confidence, we're going to put it in floating point instead of a tensor. And then here, the confidence to be attached to the string will be that floating, but only 2 decimals. So we can do it here as well. See the confidence and then the confidence string. Now this is false, so we are going to step over that. Save text is set to true. So we're actually going to step into this. And what I'm going to do is I'm going to unpack this line of code in our collab. So let's jump here, save text. And we're going to focus on this part first right here. You can see the rest is just changing the dimensions, dividing, etc. But let's focus on this piece here. So when saving our bounding box to a text file, we are converting our xyxy to xy with height. So before we actually did the opposite, we went from xy with height coming out of the predictions. We converted those to xyxy. But in this case, to save that to a text file, we want to save it in this format. We want to save it with xy with height. So we can step into this. But before we do that, this is what this function is. And we can run it here, and we could print it very quickly. Essentially, what we're doing is that conversion. There are a couple of ways of doing that conversion, and we're going to do it a little more manually here. So given that we have xy and xy, and we want to calculate xy width and height, well, let's start with the very straightforward one, the width, for example. So if we have this x and this x, well, if we subtract this x to that one, then the difference is the width. So in that case, x2 minus x1, that's the width. And then similarly, for the height, well, if we have y2 and y1, well, that difference in terms of height is indeed the height, y2 minus y1. So these are very straightforward. Now, in order to calculate x, there are 2 potential ways of doing it, and they're both equivalent. So let me show you with formulas here. So we can calculate the x and y center point directly. A line segment between 2 points, in our case x1, y1, and x2, y2, has a midpoint which is located exactly halfway between those 2 points. So you could just do y1 plus y2, and then half of that, y1 plus y2, and then half of that will give you the center point. And then you will do that the same for y. Another way of doing it is, well, using the box width to calculate that addition to x1. So you have x1, and then you add half of the width of the box to get the center. And you do that by getting that half of the width right here and adding that to y1. Now, half of the width, as we've said, is x2 minus x1 divided by 2. x2 minus x1, x1 is here, but the x are the same. x2 minus x1 by half, that's the width. So you add that width to x1. And in fact, if you solve it on the right, you get the same result. So x2 divided by 2 minus x1 divided by 1. 1 minus 1.5 is half. And then you have x1 divided by 2 plus x2 divided by 2. And if you combine the denominator, then you get the same formula. So of course, if we do that manually here, we are going to obtain the same result. So with the direct method, we obtain this, which by the way, here, they're using the direct method. You can see divide by 2, the x1 and x2, and then y1, y2, and then, well, we already talked about the width and height, pretty straightforward. But if we want to do it through the long method, where we're fitting essentially the first formula, you will obtain the same result. Okay, and I wrote it here so that you can compare. So both methods are equivalent, and then this is a 4-dimensional tensor or a vector of 4 dimensions. So when we actually perform this operation, that would be the result. So let's actually step into that. And you can see that, again, we're in general.py, and we're going to perform those conversions. You can see that we have the same values. So let's return. And then there is more to it, because here we're changing the shape. So if to that tensor, which I'm calling it xy with height, even though here we don't have that variable defined. And then here we're going to be doing some shape operations. And given that we're going to use this gn, notice that we have the width and height. So let's print this along with the shape. Then here we're going to normalize our dimensions. So here, instead of having it in absolute terms, basically for the 768 by 1024, we've gone from this bounding box or these coordinates to the x and y in the center, and then width and height. But we have it according to these dimensions, and we want to normalize that to a range between 0 and 1. So the way to do that is, given that this is x, if we divide that by 1024, then we'll have it normalized between 0 and 1. And then same for the width. The width will also follow the 1024. And then y and the height, those will have to be normalized by the height dimension. So when we run this, these values of xy with height now are normalized to a range between 0 and 1, which essentially are equivalent. It's just that if you consider the image to be between 0 and 1 on the x component, and then 0 and 1 on the y component, then, well, the point here is somewhere in between for x and somewhere in between for y, which kind of aligns with close to half and a little bit more than half, but ballpark, they're accurate. And then similarly for the width and height. A width closer to 1 will cover most of the image, and a width closer to 0 will almost be unrecognizable. And then same with the height component, close to 1 will be almost very vertical all the way to the top. So our bounding box takes a little more than half on the width and a little less than half on the height. A little more than half on the width and a little less than half on the height. Now, if you pay close attention to the dimensions, we have a tensor that is coming in that has these dimensions, essentially a 4-dimensional tensor. The output, well, we just normalize them, but it has the same dimensions. So when we convert that 4-dimensional tensor with that view to 1,4, become a 1/4 tensor. We divide it by gn, but we can see that gn is also a 4-dimensional tensor. So with broadcasting, the dimensions will be 1/4, and then we're removing 1 dimension to that to have, again, a 4-dimensional tensor. And of course, we're converting that to a list. But in terms of dimensions, we go from 4 to 1/4, which when divided by this is 1/4, but then 4 again. So I don't know if I'm missing something, but I don't think we need all those steps. And in fact, if we want to get to 4, I don't think we need to perform this operation and that one, because by dividing by 4, we already obtained that same result. So I think that view and these .view are not needed, but I could be wrong. And in fact, if you don't put those, you'll get the same result because, well, we want to get to 4, and I don't think these steps are necessary. And this is performed for every 1/4 detection. So I don't think this is needed unless I'm missing something, but you could simplify it by just performing this operation and you will obtain the same shape, the same results.